Hi guys, in this geometry review video, we'll be going over similar triangles. So first, let's go over ratios and proportions. A ratio is the comparison of two values by division. The two quantities usually have the same unit. They are usually in simplest form, and here are just some ways that ratios can be written. A cup is 4 inches tall and 0.25 feet wide. What is the ratio of the width of the cup to the height of the cup? We have to make sure that these two quantities are the same unit. The easiest way to do that is just to convert 0.25 feet into inches. So to do that, we just need to multiply by 12 to get 3 inches. The ratio is the width to the height. So we know the width is 3 and the height is 4. So this is one way you can write the ratio. Another way could be 3 over 4 or just 3 to 4. Okay, so the cross product property states that when two ratios are equal, it is called a proportion. A proportion has extremes and means. In the blue right here, those are the means, and in the red are the extremes. And when it's written in the colon format, the first and the last values are the extremes, and the two inside values are the means. So the properties of proportions are, let's say that this proportion right here, A over B is equal to C over D, can be equivalent to when you write it as reciprocals. So B over A is equal to C over D. When you switch the means, which we know is B and C, so A over C is equal to B over D. Or when you add the denominator to get the numerator and put it over the original denominator. So when you do A plus B over B is equal to C plus D over D, this proportion is equivalent to this original proportion. Moving on to dilations. A dilation is a transformation that changes the size of the figure, but not the shape. So there are two parts of a dilation. The center of dilation is what helps determine the position, and the scale factor helps determine the size. The properties of dilations are that it preserves angle measures, it preserves betweenness, it preserves collinearity, which means that points on the same line stay on the same line after a dilation. It also preserves orientation. So let's say a triangle is ABC, right, in orientation. No matter how much we dilate this triangle, the orientation will still stay the same. It maps the line segment onto another line segment whose length is the product of the scale factor and the length of the pre-image. But basically what that means is, let's say we have triangle DEF right here, right? And we dilated it to D prime, E prime, F prime. So the length of DF, times the scale factor is going to be equal to the length of D prime, F prime. That's the case for all these line segments, all the sides of the triangle. The next one says, line now passing through the center of dilation is mapped to a parallel line. So let's say we have an axis right here, and the point of dilation is at the origin, right? And say you have line AB as the pre-image. After we dilate AB, the image has to be parallel to it. So it has to look like this. It cannot look something like this, and that means it's not a dilation. Okay, the last one says a line passing through the center of dilation is unchanged. So let's say the center of dilation is point F. If we have a line going through the point of dilation, no matter how much we dilate this line, it will not change. The length and also the position will not change. So it just stays completely unchanged. Okay, moving on. How to determine the center of dilation and also the scale factor. To determine the center of dilation, first we need to line up corresponding points of the pre-image and the image. Let me just line up point A and A prime and draw a line, and do B and B prime, and then C and C prime. Okay, so on my screen, it's kind of running out of space, but if these lines were to extend, it's going to meet at one point, and that point would be the center of dilation. Okay, so to find the scale factor, all we need to do is just measure the lengths of the triangles. So let's say after we measured AC, it's 4 inches, right? And after we measured BC, it's 6 inches, and then AB is 3 inches. This is 8 inches, this is 12 inches. This is 6 inches. After we're done measuring, we can just put it in proportion or put it in a ratio and figure out what the scale factor is. AC to A prime C prime would be 4 inches to 8 inches. And for 4 inches to get to 8 inches, what do we need to do? We need to multiply by 2. So we know that the scale factor is going to be 2. And just to double check, AB to A prime B prime, we do 3 inches to 6 inches. And to get there, we need to multiply it by 2 again, right? So we know that the scale factor is going to be equal to 2. So here we have a practice problem. Triangle ABC has coordinates A, -2, 1, B, 3, 1, and C, 0, -3. On the set of axes below, Graph and label triangle A prime, B prime, C prime, the image of ABC after a dilation of 2. So all we need to follow is just x, y, and then k being the x factor, we do kx, ky. So we're going to do that for all the coordinates of a triangle ABC. So A is -2, 1.
And to convert it to A prime, all we need to do is just 2 times -2, which is -4. 2 times 1 is 2. And then B is 3, 1. And again, B prime, you just do 3 times 2 is 6, and 1 times 2 is 2. And then for C is 0, -3, which is going to be 0 times 2 is 0, and then -3 times 2 is -6. So we can just graph that. A prime, -4, 2. B prime is 6, 2. Oh, B prime. And then C prime is 0, -6. It's right here.
Okay, so this would be the image of triangle ABC. All right, moving on to similar figures. Two figures are similar if you can get one figure from another through a sequence of dilations and transformations, which include reflections, translations, rotations, and dilations. The image will have the same shape as its pre-image because dilations and transformations, they only change the size of the figure, not its shape. So you have a few practice problems. So it says, given triangle AEC and triangle DEF and FE is parallel to CE, what is the correct sequence of similarity transformations that shows triangle AEC is similar to triangle DEF? We know that there's some sort of dilation because these two figures are obviously the two different sizes. So immediately we can eliminate number 1 and number 2 because there is no dilation. Number 3 says a rotation of 180 degrees about point E followed by a dilation with a scale factor of 2. So if we were to take AEC and rotate it 180 degrees clockwise, it would end up looking something like this. And it says that next it gets dilated by a scale factor of 2, which means that it looks something like this, which is not what DEF looks like. So number 3 is eliminated. And just to make sure number 4 is correct, a counterclockwise rotation of 90 degrees. So counterclockwise this way, right? So we rotate AEC 90 degrees, it would look something like this. And if we were to dilate it by a factor of 2 at point E, it would look just like triangle DEF. So number 4 is the answer. For this question right here, we're just figuring out the sequence of transformations. So from PQRS to TUVW, there's clearly a dilation and also some sort of a flexion. So those are the main things that I want to keep in mind. We can first try a reflection over the y-axis. Okay, so first we can try a reflection over the y-axis. So if we were to reflect it over the y-axis, it would look something like this. We can try doing dilation. Okay, so we know that QP is 3 units. QS is also 3 units, right? And QR is 6. TU is 1, TW is 1, and UV is 2. Looking at the proportion, it seems about right because it is 3, 3, 6 for PQRS, excluding RS, and then the corresponding line for TUBW is 1 to 1 to 2. That is a reflection over the y-axis, and then a dilation by a scale factor of 1.3, because to get from 3 to 1, 6 to 2, you have to multiply it by 1/3. Reflection over the y-axis, and then dilation by 1/3. Let's go over similar triangle proofs. Two similar figures have corresponding angles congruent and corresponding sides in proportion. So some proofs that can be used to prove triangles similar are the angle-angle theorem, which basically means that if two angles in one triangle are congruent to two angles in another triangle, they are similar triangles. The side-side-side theorem, which is if three sides of a triangle are proportional to three sides of another triangle, those triangles are similar to each other. The side-angle side theorem, which is if two sides of a triangle are proportional to two sides of another triangle, and the angles between the two sides are congruent in both triangles, that means that the two triangles are similar to each other. And also remember that corresponding sides of a similar triangle are proportional. Moving on to the triangle proportionality theorem, when a line is drawn parallel to one side of a triangle, it creates a smaller triangle that is similar to the original triangle. So looking at the diagram below, the parallel line DE creates a smaller triangle, BDE, from the original triangle. So the triangle proportionality theorem states that if a line is drawn parallel to one side of a triangle and intersects the other two sides, it divides those two sides proportionally. So when the parallel line DE intersects the two sides of a triangle, this side right here will be in proportion to the other side. So DA over BD will be equal to EC over BE. The converse of this theorem just says that if a line divides the two sides of a triangle proportionally, then the line must be parallel to the third side. In right triangle ABC shown below, point D is on AB and point E is on CB such that AC is parallel to DE. If AB is 15, BC is 12, and EC is 7, what is the length of BD? So you have to find this length right here. So what we can do is we can set up a proportion. So 15 over 12 is equal to x over, we have to do 12 minus 7 to get this length right here, which is 5, x over 5, and we can just cross multiply. So 15 times 5 is 75, which is equal to 12x, and divided by 12, we get 6.25. So the answer is number 2. For number 4, in the diagram below of triangle PQR, ST is drawn parallel to PR, PS is 2, SQ is 5, and TR is 5. What is the length of QR? So we have to find this whole length, QR. But what we can do first is just set up a proportion using x. So 5 over 2 is equal to x over 5. So we can cross multiply. 25 is equal to 2x. 12.5 is equal to x. Remember, this is not the answer because we're trying to find this whole length, not just this one little length. So we have to do 12.5 plus 5, which is equal to 17.5. So number 4 is your answer. Next, we have the midsegment or the midline theorem. It states that if a line segment joins the midpoints of two sides of a triangle, the segment is parallel to the third side of the triangle. So line DE is parallel to line BC. The midsegment divides the triangle into two smaller triangles. So triangle AED is similar to triangle ABC, and the length of the midsegment is half the length of the third side. Line DE is equal to 1/2 BC. In the diagram below of triangle ABC, DE are the midpoints of AB and AC, and DE is drawn. Which methods could be used to prove triangle ABC similar to triangle ADE? Okay, so we know that D and E are midpoints of AB and AC, which makes this line DE a midsegment. And according to the midsegment theorem, the midsegment is parallel to the third side, which in this triangle is line BC. So these two parallel lines create two pairs of corresponding angles, this first pair being at angles E and C, and the second being at D and B. This makes angle-angle a way we can prove similarity. All three sides of the triangle ADE is proportional to ABC as the mixed segment is half of the third side. Side AE is half of AC because E is a midpoint, and AD is half of AB because D is a midpoint. So side 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 is a way to prove similarity. Side angle side is also a way to prove similarity because we have two pairs of proportional sides and two congruent angles. So 4 is the answer. We are given that ABCD is a parallelogram, EFG is a line, and diagonal DFB. Prove that triangle DEF is similar to triangle BGF. So first let's write our given. Okay, let's think about what we can prove about these two triangles. Line EFG intersects with the diagonal DFB. This creates congruent vertical angles right here. So we can say that angle DFE is congruent to angle GFB because of vertical angles. We know that ABCD is a parallelogram, so that means that these lines that are part of the triangle here are parallel to each other. So AD is parallel to CB because opposite sides of a parallelogram are parallel. Then knowing that there is a diagonal intersecting these parallel lines, we can say that these angles right here, which are alternate interior angles, are congruent to each other. So angle EDF and DFB are congruent to each other because of alternate interior angles. Now we can prove these two triangles similar to each other because we can use the angle-angle similarity theorem. Triangle DEF is similar to triangle BGF because of angle-angle. Moving on to triangle ratios, when you have a 45-45-90 triangle, it makes it easier to find the side lengths when only given one because the sides have a set ratio to each other. So when you are only given x, for example, you are able to use that value to find the other two side lengths. Just remember that the sides across from the 45 degrees are the x's and the side across from the 90 is x radical 2. It's the same idea for a 30, 60, 90 triangle. It is important to remember that x is across from the smallest angle 30 and that the hypotenuse, which is across from 90 degrees, is 2 times x and that the side across from 60 is x times radical 3. Okay, so here are just some examples. For this triangle right here, to find G and F, we have that the hypotenuse is 15. So you can just set 15 equal to x radical 2 and divide it by radical 2. And we don't want this radical 2 to be in the denominator, so you can multiply both sides by radical 2. So it'll be equal to 15 radical 2 divided by 2. So both G and F are the same value, so both G and F would be 15 radical 2 over 2. And for this one right here, you know that C is also going to be 6 radical 2, and D right here is going to be equal to 6 radical 2 times radical 2, which is going to be equal to 6 times 2, which is 12. So D is 12. For the 30, 60, 90 triangles, if this right here, the hypotenuse is 4, then we know that the smallest angle right here is going to be 4 divided by 2, which is 2. So Y is going to be equal to 2. And then X is 2 radical 3. And then for this one right here, this is 30 degrees. So this is actually our X value. And to find the hypotenuse, we just do 2 times 5 radical 3, which is equal to 10 radical 3. And to find V right here, we have to multiply it by radical 3. So 5 radical 3 times radical 3 is equal to 5 times 3, which is 15. Let's talk about similar right triangles. If an altitude is drawn to the hypotenuse of a right triangle, two triangles formed are similar to the given triangle and to each other. So form 3 similar triangles. Okay, so right here I just made everything easier to visualize. These 3 triangles right here are not drawn to scale. The original triangle hypotenuse for the other 2 triangles, this would be leg 1 and it would be leg 2. For this side right here, it is leg 1. But for the blue triangle, it is projection 1. And for the pink triangle is the altitude. And for this side right here, this is leg 2, the blue triangle. This side is the altitude. And for the third triangle, this side is projection 2. All of these similar triangles have proportional relationships with their sides. So the first one is hypotenuse over leg 1 is equal to leg 1 over projection 1. As we can see that the hypotenuse corresponds with leg 1 and also leg 1 corresponds with projection 1. Second one is projection 1 over the altitude is equal to the altitude over projection 2. So this proportion right here is comparing this projection 1 to altitude and this altitude to projection 2. And number 3 is hypotenuse over leg 2 is equal to leg 2 over projection 2. So this last proportion is comparing the yellow and the pink triangles, saying that the hypotenuse here is corresponding with the leg 2 and leg 2 corresponds with projection 2. In the diagram shown below, altitude CD is drawn to the hypotenuse of right triangle ABC, which equation can always be used to find the length of AC. So AC is this length right here, which is leg 2. So looking back at our equations, we can see that leg 2 is used in the last equation here. The hypotenuse over leg 2 is equal to leg 2 over projection 2. The hypotenuse for this is AB. Leg 2 is AC, and AC, and projection 2 is right here, AD. So looking at the answer choices, number 4 is your answer. Number 2 says in triangle SNO below, altitude NW is drawn to hypotenuse SL. Which statement is not always true? Okay, so we can just label everything. This is the hypotenuse. This would be leg 1. This would be leg 2. This is the altitude. This is projection 2. And this is projection 1. And we could just set up all the proportions. So the hypotenuse, SO over leg 1, which is SN, is equal to leg 1 over projection 1, which is SW. And then the second proportion is projection 1, which is SW, over the altitude, which is NW, is equal to the altitude over projection 2, so WO. And the third proportion says the hypotenuse, which is SO, over leg 2, which is NO, is equal to leg 2 over projection 2. So which thing is not always true? We can just go out and eliminate. Number 1 is true, number 3 is also true, and number 4 is also true because it lines up with this equation. Number 2 is your answer.